Uh, okay, so hello everyone. I am Priyanshu from Aftershoot. I work as a software engineer there, and today I'll be talking about how and why we built basically a abstraction layer for running machine learning models in Rust. And I'm about to go through the process of like why we needed this and like what we do. So yeah, before that, for a little bit of context, so who are we, what we do. So basically, Aftershoot aims to make the lives of photographers easier. So we have like two features mainly, culling and editing. So for and culling, the aim is to choose the best photos. So we run our machine learning models on your images, and we rank them based on categories like blurriness, closed eyes, emotions, and etc. So imagine you are like a wedding photographer, and you shot like 10,000 images uh, in a wedding, but you cannot deliver those 10,000 images to the customer. The customer needs the best, like 500 or maybe 1,000 images at best. So culling is a total manually process right now, but what we do is we run our AI models on AI models, and then we just rank the images, and they allow the users to choose the photos faster. So that's culling. And yeah, so this is how culling looks. So basically, this is an album, right? And you see the number here. So it says 9 and 15 on the top left. Those are the amount of duplicates we detected. So we also detect like the duplicate sets basically, and then we give them a rank. So for example, this is 5 stars and this is 5 stars. All of these are like 5-star images, and you can see like right there, we got AI selections. Ended up selecting 23 photos out of like 152. So we got down from 150 to 23 images, like in a few minutes, just by running our AI models. Uh, when you like open an image and expand it, you can also see all the key faces. So what faces are in the photo, so you can review them manually faster. So you can also see whether the eyes are open and what's the focus basically. So it really allows you to go through the photos faster and see what's out of focus, what isn't, and what are the people in the images, which can help you choose faster basically. So yeah. Okay, so yeah, that was culling. This was the first feature we launched before we had anything. So this is like the primary thing. Okay, so yeah, the next step is editing. So after we have like chosen the photos, so you have gotten down from 10,000 to like 1,000 images. So after that, you need to like edit them. We also do that. So we use the metadata info, like when you shot, you had the settings on your camera, so like ISO, exposure, aperture. We use those settings to like predict how the image should look basically to look good. We basically learn the user's editing style, so we ask the user to upload a few edited images. So it allows us to learn their style, and then we can apply their style to the photos basically. So yeah. So this is how editing looks. These are all the sliders that we change for the photo. And we apply the user style on the images. So yeah, just for some stats, we have culled 4.4 billion images, edited 1.2 billion images, and we have saved on average like 13.8 million hours for all of our users combined. So that's great. That's approximately 1,600 years of work. So yeah. So this is all well and good. So back then, our architecture was something like this. Okay, so our backend was in Rust even before also. The backend was responsible for like project management, so like creating projects and all of that stuff. Running the AI models was a different binary. So there was a culling binary for culling, and there was a binary for editing. And these are both like written in Python. So we used PyInstaller to make a binary, and then we basically use like inter-process communication (IPC) to communicate to them. So the backend would make calls to the culling binary, and the backend would also make calls to the editing binary. And this worked really well. because our models need to run on the user's machine. We don't upload the images to the cloud to run models on them. We run all our models locally on the user's machine itself. So yeah, this calling binary system with the backend worked pretty well for a while, but then came retouching. So retouching was our third major feature after culling and editing. So what retouching includes is basically you select the face and then you tell it to like remove the acne, for example, remove the blemishes from the image. So unlike culling and editing, which happen on multiple images at the same time, retouching is a much more like per image process. So you need to open up the image and tell it to, like from this image, remove the acne, for example. And the feedback needs to be fast. So when I move the acne slider, when I move the teeth pattern slider, I need to see what it did to my image. Otherwise, it wouldn't make sense. So at that point, IPC and Python were too slow because unlike culling and editing, which is just a batch process, basically you will like put culling for 10,000 images, it will take like 30 minutes and you will forget about it and leave it. And you will come back and it will be done. It was still slow, but it wasn't a problem, basically. But for retouching, it's a problem because you need real-time updates to see what's happening on your image. So the IPC and making different binaries for models was no longer a thing we could do. So we had to go back to the drawing board, basically. What slide is this? Yeah. So now our front end, which is an Electron, will communicate directly with the backend, which will be entirely in Rust. All our models, all our inferencing will happen in one backend. So when we have all the image buffers in the same memory space, we don't do IPC or anything. It's going to be faster, basically. So it will allow us to do retouching. But there was one issue with that. So yeah, how do we run our models in Rust? So that was the challenge we faced, because in Python we use like PyTorch and stuff, and like there was like reputed libraries which allowed us to easily run our models. But for Rust, it wasn't so simple. There were a bunch of libraries like Candle, but they didn't entirely support every single operation in our model. So we couldn't just use them. We had to build something of our own because our use case was really special. So yeah, so the inference engine came from that. So we had to build our own inference engine to run the models and stuff on the user's machine in Rust entirely. And we had to make it cross-platform because our users are on Mac OS and Windows. So it has to be cross-platform, and it has to support all the like special architectures of NVIDIA, Intel, and AMD. So for that, the inference engine we ended up building has a really unified API. So what you do is you just read the model file. So for example, model.onx, and then you just make a pool. So you just pass in the model the config options, and the config options have lots of options. So you can use ONX CPU, you can use ANE, you can use CoreML, and then you just pass in the input and you just tell it to predict, and you just get the output. So it's really seamless and really easy to run inferencing. Because we had to make it cross-platform, we had to support different architectures. So these are all the different architectures we support. So basically, MNN, ONX, CoreML. So MNN is CoreML, ONX is used on Windows, and CoreML is like Apple's own neural engine to run the models on Apple systems specifically, like silicon chips. So yeah, and our model API is also like trivially simple. We just load, there's just load, unload, is loaded, and predict. So we really, with using Rust, we aim to achieve a really seamless experience for the user. So you can just call predict and not have to worry about what backend and what exactly the optimizations are gonna be used. This is the type that's passed to the model. So it's just a ML array as long as it implements all of these methods. So it has a D type, which is basically a dynamic D type. It has a shape. It has a to-end method. You can use this as an input to the model. So yeah, and yeah. So about the performance, or the ONX runtime for the CPU is like 1, and CoreML A&E. So CoreML is Apple's own neural engine. A&E stands for Apple Neural Engine, and that's like 6 times faster than CoreML and Onyx runtime CPU. So yeah, and editing and culling also got 5 times faster on average because of the rewrite we did in Rust. So why we chose Rust for this? So Rust allowed us to really build our own. So Rust allowed us to build like a safety net of sorts on the models, and allowed us to really build a safe API around running the models and stuff. So yeah. Wait 1 second. Okay, so yeah, thanks. We do check out our open source stuff. We are gold sponsors of this event. The the backends we use for FFI, so MNNRS and CoreMLRS are open source, and patches are welcome. We also have NDCV bridge. So yeah, do check out our booth. And yeah, thanks. And that's all. And yeah, if anyone has any questions, yeah, can you pass the mic?
So you explained the interfaces. Could you also go into how you're actually running the inference in Rust?
I'm sorry?
Could you also go into how you're actually running the inference?
Uh,
The actual mathematical part where the computation happens for the inference. Did you make that, or are you using something?
okay, so yeah, so that's what MNN RS and CoreMLRS is for. So they're already, the engines already exist. So MNN and CoreML, for example, are the engine. So we built safe FFI bindings. So these are C++ or C libraries. We built
Okay.
bindings, safe bindings over that to be able to use that in Rust.
Got it.
Any more questions? Yeah.
Hello. Okay, so you mentioned about FFI binding.
Yeah.
How you achieved that part in newer, when you have the native language C++ something?
Yeah.
You mentioned safe part. So how you make sure that is safe?
Okay. Uh, Great question. I think Swarnim can answer that better. Yeah. Can you pass it? Oh yeah, I think Swarnim can answer that better though. Yeah.
Yeah, so for us, safety as a standard works on a layer directly coupling the bindings to the APIs. So when we built MNNRS, we built CoreMLRS, we built either a sys layer or a systems layer, which directly creates bindings on top of the frameworks and APIs that we want. MNN is a framework for machine learning, and CoreML is a similar one. Similarly, Onyx has a framework which already exists in Rust, which is ORT, and that builds its own safe APIs. How we do it is largely we split up two different parts, every API into two different parts. First is the state logic, and then is the actual FFI or the memory transferring and like memory sending the buffers, getting the buffers back. How do you share them, and how do you manage the ownership? So those were the big semantic challenges that we have built around. And largely we have added a lot of guarantees around both type safety in terms of how the model states are executed. And we have added a lot of type safety in terms of how the exact execution inside a runtime would work with the send sync features, the concurrency, the fearless concurrency, and all of those things. Largely, all of those features are implemented in the libraries themselves, low-level libraries, but we provide a unified API and an interface to interact with these libraries through our inference API layer, which does two big, large tasks, which is managing the dynamic typing for all the different types of models that are around. Like all the like quantized models, all the very like large models, LLM type models, generative AI models, very small niche models which have very different kind of input parameters and different input shapes. And the second part is like on the inference layer, we have added another layer of as a concept of defense in depth, a safety layer where each type that converts has some kind of safe API wrapper. Like for example, you saw some kind of a middleware type for our input and output interfaces, which is in input type or output type. And these are generally generalized on top of some kind of a tensor, or like a better explanation is just an array type in ND array. And how we build these is we use slightly hand wavy logic around defining some rules on what types are actually convertible across each other. And once we have those set of rules, again, these rules are like verified by us manually, and we have implemented them using memory unsafe patterns. And then we have just implemented those, and then we have implemented them both as a ownership model with like two owned, as you see, and a try as pattern. Again, the code, our exact code doesn't look exactly like this, but it's largely the same. We have a fast path where we take lifetimes, borrowing, and there's a slow path where we do an allocation. Again, allocations aren't really slow when we are talking about ML models, but there is still a cost when you are doing hundreds, thousands, millions of images. Some of our customers are processing tens of thousands of images every day. So that adds up really quickly in the time saved. And because we are running entirely on edge devices, that makes some sense, I think.
Yeah. Okay, so yeah. So if anyone like wants to know more and has more questions, you can check out our stall. It's right behind Audi 1. So yeah, that will be it from my side. Thank you, folks.